Hi everyone and welcome back to Physics 11. So in this video we're going to be looking at kinetic energy, and hopefully this is going to be a review for a majority of you from grade 10. So kinetic energy is the energy of motion, or energy of moving objects. So it's a scalar value, so it's the same as potential energy in work, and it's going to be measured in joules or Newton meters. Now, the equation for this is, again, I'm going to use the subscript K to indicate energy that's kinetic, and this is going to equal to 1/2 times mv squared, or mv squared divided by 2. So, where m is the mass of the object and v stands for the speed or velocity of the object. So again, the 1/2 just means that we have the m and the v divided by 2. So that's going to be our equation for the kinetic energy. Now, one thing I should mention also, some of the notations you might encounter in other textbooks sometimes is they use P for potential and energy, U for potential energy, or EP. So all these can be potential energy. And so same thing applies to kinetic energy. Some textbook will use KE, V for kinetic, and of course we're using just the subscript to be more explicit, and that's kinetic. So just in case you encounter some resources or some other videos where you see these, just so you know what those mean. So anyway, let's take a look how we can use this equation. So here's an example. I have a 60 kilogram student is running at uniform speed of 5.7 meters per second. What is the kinetic energy of this student? So we need to know the mass, we need to know the speed. So in this case, our mass is 60 kilograms, so 60.0 kilograms, and our velocity is 5.70 meters per second. Now notice the units have to be in meters per second for the speed, and of course mass has to be in kilograms because our metric units or SI units that we need to have are kilograms, meters, and seconds. And then all of the derived units have to have those as well. So our kinetic energy, so E subscript K, is going to be m times the velocity squared over 2. So we're going to plug in our mass, so 60.0. Now, one thing that people often forget is the square on the velocity. So don't forget to square the speed here, or the velocity, when you do the calculation. And then you're going to divide this by 2. In this case, let's see, we have 3 sig figs, 3 sig figs, so the answer should have 3 sig figs in the final answer. So this equals to 975 joules. All right, so that's a simple way of finding the energy. And of course, once you know the energy, if you know, for example, the force that the student is applying, then you can find the distance traveled or something like that. So it's really easy sometimes to go from energy concepts to dynamics concepts, and then of course you can also use kinematics to find any other pieces of information. Okay. Now here's another example. It says the kinetic energy of 2.1 kilogram rodent tomato is 1 times 10 to the third joules, so basically 1,000 joules. How fast is it moving? So let's say someone threw it. So in this case, what you're given is the energy, right? So you have the kinetic energy, which is 1,000 joules. So if you want, you can write it as 1,000. Still going to be, actually we have to use the decimal because we do have, these are significant zeros, so we can't just convert it to 1,000. Times 10 to the third, and this is joules. We know the mass, which is 2.1, and the velocity is what we need to find. So v is the unknown. Okay, so here's our equation. Okay, now we want to solve this for v. So we're going to multiply both sides by 2. So we get 2 times e equal to mv squared. And then divide both sides by m. So we're going to end up with 2 times e over m equal to v. And the final step is to take the square root on both sides. So which means we're going to end up with the square root of 2 e k over m equal to our velocity. So the velocity in this case is going to equal to 2 times 1.00 times 10 to the third over the mass, which is 2.1. Okay, so you have 3 sig figs on the top, 2 on the bottom. The answer should have 2 sig figs, and in this case we get 31 meters per second for the speed of the tomato. So again, this is just an example how we can manipulate the equation to find one of the other variables. So how can we relate kinetic energy to other types of energies and work? So for this we have the work energy theorem. And if a net force acts on an object, then it must be accelerating. Okay? Otherwise, the object is going to be either at rest or it's going to be at constant motion. So it's going to be moving at constant speed. So this acceleration is proportional to its change in kinetic energy. And therefore, we can have the equation that we used in the past with the potential energy, that work is defined as the change in kinetic energy, or in this case, the force, the net force, times the distance. Or in this case, we should really just show perhaps the change in distance. So delta D. So let's see how we can use this relationship to solve some of these questions. So a sprinter exerts a net force of 260 newtons over a distance of 35 meters. What is his change in kinetic energy? So in this case, we're looking for the delta E. We're looking for this delta E. In this case, this is kinetic, so we're looking for the E subscript K. So we're going to use our equation that we just showed here. So our F net times D, or really I should write change in distance, so delta D. Okay. Now we already know what this change in distance is going to be. It's going to be 35 meters, right? And we know what the net force is. So the values are already given. So we don't really need to split this into final minus initial, because you're given the values right away. If, for example, you were given just the final and the initial, then you might have to add that extra step to show that you find in the delta D, or in some instances might be the change in force as well, but we're not going to be actually dealing with changing force in high school physics. That's going to be more once you do some calculus. So for now, all we have to do is just plug in the values. So it's going to be 260 newtons times the 35 meters. All right, so we have 2 sig figs here, 2 sig figs there. So the answer should have 2 sig figs because we're multiplying. So we're going to round this to 9100 joules. All right. So let's take a look at one more example. In this example, a student pushes 25 kilogram crate, which is initially at rest. So remember, initial rest means your V initial is 0. A force of 160 newtons over a distance of 50 meters. Okay. If there is a 75 newtons of friction, what is the final speed of the crate? All right, so what do we know here? Here's the equation we're going to be using. So again, delta E equal to F net times our distance. So in this case, we know that, let's see, initial velocity was 0. So we know from here that our V naught is 0. If your V naught is 0, therefore your kinetic energy initial is going to be 0, right? Because if you plug it into the equation 0 for velocity, right, if you have your initial mv squared over 2 and end up with 0 on the top, everything becomes 0. Which means that your delta E, you can write it out as, of course, as EK final minus EK initial equal to F net times D. But in this case, we know that this is going to be 0 because our V naught is 0. Okay, so all we have left is just the kinetic energy at the end, so the final kinetic energy. So which means that we're going to replace this EK final with the mv final squared over 2 equal to our F net times the distance. And from here we can then solve for the final speed because we're looking for the VF here. So we know the mass, 25 kilograms, and we know that the net force is 75. The net force we need to actually find. So we're going to replace our values, solve for D first. So let me do it here. So let's solve this for the velocity, which means we had to multiply both sides by 2 and divide by m. So we're going to end up with V final squared equal to 2 times the F net times D. And let me not skip steps here. So then we divide both sides by m. Times D. Divide this by m. All right. And the next step is to square root this. So let's take the square root of all of this. All right. So what do we got to do here? So we need to now plug in the values for all this stuff here. So let's write on the side here, let's make a little diagram, our free body diagram, and indicate all the forces so we don't forget what we're dealing with here. So we have our applied, F applied, and we have our force of friction. And of course, in this case, we'll have a normal force, and we have our force of gravity, okay? So from here we can write our F net. So our F net in the x direction, so let me use the sigma notation here to show that this is in the x direction. It's just going to be the FA minus the force of friction, right? Now, because they're moving it, we're given the actual value, so we don't need to replace F of friction with mu times Fn, and because also we're not given the friction coefficient. But if you have a question that's like that, then you have to do that extra step there to show that force of friction calculated from the normal force and the coefficient of friction. So then we know that this is going to be plugged in here when we do our F net. So in this case, we have 160 minus 75 newtons, and this equals to 85. Okay, so our F net, our MA here, is going to equal to 85 newtons. So that's what we're going to plug in into our equation for the final velocity. Or you could have showed this, you could have plugged in here into the equation for the velocity as well, but because this kind of dynamic section, we can do it separately and then deal with the calculation for the velocity here. So let's plug in our numbers for the Fnet, which is going to be 85 times 15 meters over the mass of 25 kilograms. And then all of this, we have 2 sig figs, so the answer should have 2 sig figs. So the answer here is 10, and we have to add the decimal point here to show that we have 2 sig figs so you don't drop the 0 here. So we have 10 meters per second as our final speed. All right, so as you can see, our definition of kinetic energy is pretty useful, especially when you're dealing with moving objects. And of course, we can relate this to dynamics. So as you can see, we're using our work definition and our energy definitions to find a lot of these questions that normally would probably take quite a bit more work if it was dynamics. And this is going to be more evident once you do some of the questions, for example, on a slope or stuff like that. So there are some practice questions in worksheet 7.3 in your notes. So make sure you do those questions. And again, if you have any questions or you want me to go over any of these, make sure you post a comment on Teams so then I can make a separate video on that. All right. And again, you can read the sections from the textbook on kinetic energy, and I'll probably post the page numbers so you can find it easier. Okay, so that's all for now.